Horses are described as hooved, odd-toed ungulates, which belong to the order Perissodactyla and the family Equidae. These mammals share their order with rhinos and tapirs and represent a prime example of quantum evolution. This form of evolution concerns high-level evolutionary patterns that occur on timescales ranging from thousands to millions of years, and with their fossil record dating back 55 million years, Equidae certainly fill this criterion. The history of the horse family began during the Eocene epoch. During this time was the first ancestral horse appeared. This primitive animal was commonly called the Eohippus or the dawn horse. It stood at about 45 centimeters tall and was characterized by an arched back with raised hindquarters. Its legs ended in padded feet, with 4 functional hooves on each of the forefeet and 3 on each of the hind feet. The Eohippus then gave rise to many now extinct branches of the Equidae family. So let's explore some of the major groups that precede the modern-day horse. The Mesohippus was the next important ancestor in the evolutionary timeline of horses, with their fossils found in the early and middle Oligocene. Mesohippus was far more horse-like and stood at about 61 centimeters tall. It had a muzzle-like snout and legs that were longer and slimmer. Towards the end of the Oligocene, the Mesohippus had evolved into a larger form known as the Miohippus. Descendants of the Miohippus split into several evolutionary branches at the beginning of the Miocene epoch, and the first representative of the modern horse line was the Parahippus. This horse and its descendants marked a radical departure, as they had teeth that were adapted for grass eating. Towards the end of the Miocene, the change from a grinding to a grazing dentition was completed in Merychippus. This horse, which evolved from the Parahippus, stood at over 100 centimeters and had a skull that resembled that of the modern horse. What's more, the long bones of their lower legs had fused and provided adaptation for swift running to evade predators. Finally, at the end of the Miocene, Merychippus gave rise to Pilohippus, which was the direct predecessor of Equus, the single-toed horse genus that we are familiar with today.
One important evolutionary trend leading from ancestral to modern horses is the deepening of the cheek teeth from small primitive mammalian condition of brachiodonty to hypsodonty. Hypsodont teeth are high-crowned and adapted for grazing grass, while brachiodont teeth are leaf-crushing. The earliest horses from 55 million years ago had short-crowned molars with poorly developed sharing crests. The form of the teeth suggested a frugivorous diet. During the Eocene and Oligocene, horses acquired sharing cloths on their molars, suggesting a shift towards leafy browsing. The subfamily Equinae, which includes living horses, appeared in the early Miocene. The first representatives showed increased crown height, but they were still called mesodonts, whereas high-crowned hypsodont horses appeared millions of years later. As already mentioned, this was not a gradual process leading to the modern horse, and characteristics of grazing dentition appear abruptly in the fossil record, rather than as a culmination of numerous gradual changes. It is generally accepted that the increase in tooth crown height represents an adaptation against tooth wear resulting from an abrasive diet consisting primarily of grasses. The teeth themselves are not more durable, but rather there is more tooth material, therefore it takes longer for it to get worn off. A part of the crown is retained within the jaw, and it will erupt later in life as the exposed portion of the crown wears down. Digit reduction is a repeated theme in tetrapod evolution. One of the most extreme examples of digit reduction is the modern horse, which evolved monodactyly, a single toe from an ancestral state of 4 digits. Hyracotherium were the first ancestral horses which appeared in the early Eocene according to the fossil record. The species from this genus had legs with 4 functional hooves, and later in the Oligocene fossils of Mesohippus indicated a more horse-like physiology. The foretooth on the forefoot had been reduced to a vestige, so that both the forefeet and hindfeet carried 3 functional toes and a footpad. During the Middle and Late Miocene, transitional fossils indicate the ancestors retained the 3-toed foot, and it was not until 4.5 million years ago that the genus Equus, leading to all modern horses, evolved from one of the 3 evolutionary trees.
Almost all literature hypothesizes that the evolution of monodactyl must relate in some way to an improved form of locomotion and an increase in body size, although the specific underlying driver for monodactyl has been debated. The classic explanation is that monodactyl evolution was an adaptive response to changes in the landscape, shifting from forests to grasslands. Characterized by open spaces with hard ground, evolution selected for horses with longer, more slender legs to facilitate running at greater speeds to escape predators and decrease the energetic cost of locomotion. The alternative hypothesis is that evolutionary increases in body mass produce greater bending forces on the limbs, which selects for a single digit over multiple as it has greater resistance to bending forces. Studies on beam strength and the likelihood of fracture failure of equid metapodials found the beam strength of a central metacarpal in Equus was much greater than any tridactyl equine. The central metacarpal was capable of sustaining stress for both equus and tridactyl equines. However, when simulating a gallop or jumping, only equus and 3 of the tridactyl equines could support it. However, evidence is not unequivocal for body size as the key evolutionary driver, as this extant equus was fully tridactyl and could reach 500 kilograms in weight. Another anatomical feature correlated with monodactyl is the change from a more flexible back to a stiffer one, with the anterior and middle lumbar flexibility decreasing throughout equid evolution. However, again, body mass cannot be the only evolutionary explanation, as Old World Hippoparionians remained not only tridactyl but also had a more flexible lumbar region than equus. This spinal anatomy was perhaps retained as its original woodland habitat required it to make sharp turns while running.